Hello guys, welcome back to my channel, Gamma Di Gamma. In today's video, we're actually going to do quite a straightforward problem. You might have noticed I'm still getting warmed up after I've come back from my long break. But I saw this problem in a bunch of places on Instagram, on other YouTube channels. I thought we should do it and maybe sort of slightly extend it. So with that, let's get started. So as always, let's define the integral that we need to solve. So of e to the 2 cosine of x dx. First of all, it's non-elementary. Otherwise, I really wouldn't do it on my channel. And second of all, the form that it's in is not really going to help us. So we can do one thing. We can use the symmetry of the cosine over the interval minus pi and pi to write integral from 0 to pi as one half of the integral from minus pi to pi. Now this is only because of the fact that the cosine function is even. Now you will see when we do the second part of this video, the second integral in this video, that we cannot really use this evenness of whatever function we're going to have. But for now, it suffices. And we can do one more thing. We can break down cosine using Euler's identity. So we get e to the ix and added with e to the minus ix, which I can just separate out like this, dx, obviously. And then what I'm going to do is I'm going to expand the second cosine in its infinite geometric infinite power series. So we have e to the ix sum k equals 0 to infinity of e to the minus ix to the kth power over k factorial dx. And now, using the arguments of uniform convergence of this function in general, it's quite easy to make the argument of uniform convergence, because we have indeed here e to the minus ix, which is always bounded by 1. And with an upper bound of 1, we see that this in a infinite series actually converges, and then that's all we need to justify moving this infinite sum outside and the integral inside. I'm not going into the details of the analysis here. Many people actually hate me for that. So we have this in place, and then the integral is as it is. e to the ix e to the negative ikx dx. And now we can just do, there's too many exponentials, so we can just do a substitution. So the substitution is z equals e to the ix, dz is iz dx. So the integral actually is 1/2 sum 0 to infinity the k factorial term, and we actually have a closed contour, which is the unit circle in the z plane. e to the z, z to the minus k over iz dz. Okay, let me just rewrite this a little bit. I hope you see how we get this unit circle integral. It's because our z is actually the exponential e to the ix, and at minus pi and pi we're actually just rotating around in the complex plane, a full circle of radius 1. So we have this divided by z to the k plus first power dz. Now what are we going to do? Well, we actually have a contour which is a unit circle, but the problem is we have to use complex analysis on it, and complex analysis says that it's just 2 pi I times the sum of the residues of the devaluated at the pole of the integrand. Well, the only poles that we're going to have actually come from this denominator, so they're happening at 0. Z equals 0 are the only poles, but then they're not simple poles, they're kth order poles. So I'm just going to remind you what the formula for the nth order pole is, because I know it's been a long time. I also needed to sort of revise my formulas, believe it or not. So nth order pole, for an nth order pole at say some point z0, so if you want to find the residue at this z0 of some integrand that you have, which is say f of z, you're going to have 1 over n minus 1 factorial, limit as z goes to z0 of the nth derivative, sorry, the n minus first derivative of z minus z0 to the nth power times f of z. Okay, wonderful. Now we know what the formula is, and now we can just directly apply it to the expression, the integral we have. So, while the 1 over 2i can be taken out, we still have the sum from 0 to infinity, and 1 over k factorial. But now we're going to have a 2 pi I from the, because we have the 2 pi I from the residue theorem, over the k factorial from the the factorial in the formula that I have above, limit as z goes to 0 of the kth derivative of well, just e to the z, because the denominator will actually cancel out nicely. With that, we actually see that we're going to get pi times the sum from 0 to infinity of 1 over k factorial squared. So you see, we can't really evaluate this further. I think I'm going to leave my answer to this this final form.